Hi there, math fans. I'm on kind of a circular motion kick here. So I was thinking about the spirograph video I just made over the course of this day, and I was thinking this is the exact same thing as the teacups, almost. So if you don't know what the teacups are at Disneyland, I think it's called the Mad Tea Party Ride. We've been lucky enough to go to Disneyland a couple times. Here we are when our kids were much younger, them riding the rides with my mother-in-law. Here's my sister-in-law and brother-in-law and a couple of their kids riding. And I have a lot more pictures and videos. They all enjoy it. I don't enjoy it because I get sick and throw up whenever I spin too quickly. So for me, I always watch and take pictures. Based off of those pictures and a little bit of help from Google Photos, I was able to pull some measurements. So I estimated some measurements so that I could get a somewhat accurate picture of this, and then I'm going to show you some visuals here in just a second. But the bigger picture is this. I'm not going to do a full animation. I started to realize that was going to be too hard, but I do have an animation of one person riding the ride, which I will share with you in a second. And I will, like I've done with my other motion videos, I will share a link in case you want to play around with it and make it better. So what I realized as I thought about it is the teacups ride is a big merry-go-round problem. Terrible at drawing circles. We have this big outer circle, which is the outer edge of this thing, and it spins. Viewed from above, it spins counterclockwise. I went back and looked at some of my family videos to figure that out. And I actually counted. So I paused the video, I labeled a point, and then I let the video run forward. And I realized that it did one revolution in about 16 seconds. So I'm trying to give realistic examples. Again, my goal here is to give my students a better appreciation for circular motion, because so many students get confused by this. They always want me to review, and I hope by having these videos ready, it can help motivate. I found out the radius, if my Google Images visual is right, I got that this was about, and surprisingly, you can't find this information. I couldn't find it online, so I just decided to go get it myself. Maybe they'll come after me now. I don't know. Anyways, and then we had this inner circle here, but that would be a story. Disneyland gets mad at me for making this video. Okay, so then we had this other circle, and that's the circle that some of the teacups are on. And there's another one over here, and another one over here. That's these three. 1, 2, 3. And each one of them has 6 cups on them. But that, again, I measured and estimated. Again, by looking at family videos, I saw that this goes clockwise. Each of these goes clockwise as this thing spins. And I looked at that as well by following one of the teacups my family was on. In a video, I realized this did one revolution in 11 seconds. And I realized we can definitely model this. I estimated, I feel like some of these things were a little less accurate, but I estimated what the radius of this was. And where did I write that down? It was 8 feet. And then lastly, you have the teacups. So I tried to measure that as best I could. They overlap slightly on the side, and they have some center. Okay, and those had a radius of about 3.5. So from that, I constructed a bit of a model. I did, and I'll go through these visuals in a second. This is when I got right about here, and I stopped developing it. So I took all those measurements, I put in 6 teacups viewed from above, and I decided at that point to stop drawing it accurately anymore. And then I removed these, and I decided I would just study one of them. Okay, so from here on out, I'm going to pretend that you get on the teacups right here. And then we're going to study the motion, and then I'll show you an animation, and then I'll share this with you. Okay, so here we go. So for the rest of this problem, here's what we're going to do. Let's erase these other circles. And let's draw a coordinate system. Let's make this coordinate system pass directly through here. This is the y-axis. And let's start labeling things. So let's call this, the radius of this was 8. From my measurements, this was 13, 0. Meaning it was 5 units this way. I'm going to assume that the center of this, I should draw it better. So let's erase this and this. Did not mean to erase the whole thing. The center of this will be 21, 0. Sorry, I'm looking at my notes. That was the center of this other circle. The radius of that circle doesn't really matter, but I think I had it as 3.5, so it would be 24.5 would be the edge. But I'm going to pretend I have a person right here, that they're 2 feet from the middle, which may be about right. I don't know, 2 feet over, 1 foot, 2 feet. Okay, so we're going to say the person is at 23, 0. So this is the beginning, and then we're going to track the motion of that one person on that one ride. Okay, so here's our chance to do circular motion yet again. I'm going to move these out of the way. Those were my measurements I made. Okay, so here's the circular motion. We're going to one by one and track where the centers go. So let's call that the first center we want to track. The center of, I don't know what the word is, that turntable. Okay, so what can we say? As this thing goes around, it's always going to be 13 units from the center. So this is going to be the radius. And the formula I'm using, yet again, is, in general, it's the center plus r cosine of theta plus r sine of theta, as I've discussed in my previous videos about circular motion. So this is going to be 13 cosine of theta, 13 sine of theta. Now I left the angle blank because in this case I can actually replace it with what the angle will be, because it's going to be 1 revolution every 16 seconds, which is the same as 2 pi radians every 16 seconds, which is, if you want to simplify it, it's pi over 8 radians per second. So what that means is you need to take pi over 8 and multiply it times the number of seconds the ride has been going. That will give you the angle in radians. So what I just discovered is where this will be after a certain number of seconds. After 16 seconds, it will be all the way around, which is the same as 2 pi. It's a nice little way to check your work. If you plug in a 16, do you get 2 pi? Yes. Okay. So that just describes the center. But now we're essentially done with this big circle. We can just study, we're done with this too, we can just study the blue circle. So now let's talk about the center. In fact, we're done with the blue circle too. Let's talk about the center of this little purple circle. Let's call that x1, y1. So x1, y1 is going to be whatever its center is, which is this one, x0, y0, plus, and then we need to know the radius. So the radius being how far we are from the center, which in this case is 8 cosine of the angle, sine of the angle. Now in this case, an interesting, if you were just looking at that purple circle, it's going this way. And that's from the observation of the fact that it's going counterclockwise. So we know how it's changing. It's doing 1 revolution every 11 seconds. So that's going to be 2 pi radians. Let's convert right away over 11 seconds. But since it's clockwise, it's going to be negative. It's like it's subtracting. So it's going to be negative 2 pi over 11t, negative 2 pi over 11t. But cosine of a negative is the same as the cosine of the equivalent positive, and sine of a negative is the opposite. So the way we can write this at this moment, let's kind of stop and assess. The center of the purple circle is given by x0, which is 13 cosine pi over 8t, plus 8 cosine 2 pi over 11t, and then 13 cosine. It's just circular motion. Yeah, there's a lot of circular motion going on, but we can handle it. And now I'm down to just the purple circle. And what can I say about the purple circle? Now the purple circle, how fast it's going to spin and whether it spins this way or this way depends on the people sitting in there. You control it by turning a thing. So I'm just going to leave that as like an F, your frequency with which you turn it. How many revolutions you want. So this is going to be how many seconds it takes you to do one revolution. One revolution in F seconds. You'd have to adjust the flow. If you're going to go clockwise, you'd have to treat it as negative. If you go counterclockwise, you have to treat it as positive. For my animation, I'm just going to make it a relatively a number that gives a nice visual. Okay, so finally, I want to study this person that is 2 units from that center. So now we're down to the bitter end here, which is we need to take the center of that circle and then add this person that's 2 units from there, and then do 2 pi over ft and sine of 2 pi over ft. And that's the formula. This plus this is the teacups formula. So I was pleased when I thought of that today, and I was like, I could solve this once I can get the measurements. So then I worked hard to get the measurements because I thought it'd be a fun example to have for many years to come. Now I'm going to show you what happens when you graph that, and then I'll share that with you so you can do the teacups. If someone wants, they could put the other circles in there, but it's a bit of work to sort of draw all the circles, figure out where all their centers are, and then think about how to animate every single one of them. And when I realized the work that would be involved just in the sheer matter of typing in those 18 circles, I decided to not do that. So what I decided to do instead was just this. So here's this precise situation. I picked f equals 10, that we're going to turn that thing and we're going to complete a rotation based off our turning in about 10 seconds. Okay. And then I set everything in motion. That took a bit of work for me to do that, but that was within the realm of what I could do. Let's slow it down and set it going. I made a little person out of emoji symbols. Here they go. Spiraling around this thing. The ride actually goes for about 90 seconds. And this is a pretty accurate depiction of what you see from me watching my family many, many times do this. I realized I had one more graph I wanted to show, and I will do that now while you're watching that animation. Okay, here we go. Off we go. There's the path this person follows. And it's kind of a type of spirograph, except you have a gear within a gear attached in an interesting way. This is the path you take. The path that I will never take because I get so ill when I do this. Interestingly, it kind of looks like a star. So that's kind of fun to see. So this is the teacup pattern you follow. because of the little extra turn, you don't quite get a spirograph. You get these little loops in a couple spots. So here you go. You keep going for 90 seconds. I'm curious what it looks like at the end. I didn't do this ahead of time. I feel like I'm thinking of lots of interesting questions here. So the interesting question for me that always was taking pictures is, where should I stand to see them? Based off of their starting position. I feel like at the end of this we'd be able to answer that question. So if they start on this far edge, it looks like if you stood here, they'd come close to you 3 times. So whatever place they're at, you should go, 90 degrees counterclockwise from them. And you're going to get to see them 3 times. So there's an application. Or you could go about 180 degrees counterclockwise from them. There's a few spots, but those are going to get you pretty close to them. So there's the takeaway from this. When you see your family get on, of course it matters which one they're on. You'd have to run more experiments. All right. Hope you found that interesting. I certainly did. And thank you for listening. Give me a like if you like that. I have several more circular motion problems to describe for you. Okay.